Welcome back, mathematicians. Let's talk about the difference between scale and a scale factor. So we've been talking mostly about scale factors in lesson 6. And what's true about scale factors is there's no units. Right? It's usually just 2, 3. It's not like 4 inches. Scale factors describe how many times larger one object is. It could be smaller. And we use that to compare the sizes of two objects. It differs from scale. So scale has units, right? It's like this, on this map here, this 1 centimeter actually represents 2 miles. Okay, so those are units, right? Centimeters and miles. And we use scale to describe how much a specific distance represents. Okay, so not how much larger an object is or smaller an object is, but what a distance represents. So scale is more the comparison of distances rather than scale factor, which is a comparison of sizes. What they both do is they both describe objects at different sizes. And both of those numbers really represent how big or smaller the drawing is. So you can get a sense of how big the actual object is from both of those, scale and scale factor. But we use scale actually a lot more often than we use scale factor. And part of it's because scale is usually like a real world scenario, especially when you're drawing something or you're making a map or you're doing blueprints. And that's what we're going to find in this lesson here. Now take a look at both of these examples. So these are two drawings of a coffee cup and the subway lines around Boston. So on the left you see that there are some scale drawings, and on the right you see those are not scale drawings. Now, what do you think makes them examples and non-examples of scale drawings? Now I want you to put your thinking into the share with my class slides. And now that you've written your thoughts, let's discuss. So what you may have seen is that scale drawings are more detailed and precise. Sometimes even we have labeled measurements like the 13.2 centimeters, but there are none here, right? Scale drawings represent what's actually in the world, so actual distances. Which is why you'll see that this, while it's a straight line, doesn't really represent what's actually happening with that railway. And then scale drawings give you a much more complete picture of the actual object, which is true because this one is more detailed probably than this one here. So you might see one like this that I'm circling right now, the non-example of a scale drawing. You might actually see that more clearly on the map of the actual subway when you go to Boston. And that's because it's easier to read, right? It's easier to go this stop, then that stop, then that stop, rather than have a curve and bend. But when you're trying to survey something or get more of a sense of how far stops are away from each other, things of that nature, we want a more realistic picture, so we go with an actual scale drawing. So this is activity 1 in workbook page 26 to 27. Karima creates a scale drawing of the basketball court she wants to build in the local community park. The park's board of directors approved building the court in a 20 by 20 meter area of the park. And we want to see if this version that Karima has built, will this vision of the basketball court fit in the designated area? So I want you to take a second and think about whether or not you think this will fit in a 20 by 20 meter area of the park. And I want you to put those thoughts in the comment section of this video, or wherever it says share with my class. So what we need to figure out whether or not that basketball court will fit is we need to measure. So she has made a blueprint for us, a scale drawing, and we want to see if that actually can fit into the spot. So what you need to do is you need a ruler, um, and I just have a digital ruler here, and we're going to fill this out together. We're going to go through activity one together. So it says, here's a scale drawing that Karima presented to her neighborhood parks board of directors. The scale of Karima's drawing is 2 centimeters to 5 meters. Explain what this means in your own words. So what that means is that in Karima's drawing, every 2 centimeters represents 5 meters in real life. So every 2 centimeters on the drawing represents 5 meters in real life. So what we're going to do for part 2, or number 2, is they're asking us if it will fit in the court. So we're going to go through and you're going to take your ruler and you're going to go through and you're going to measure each spot that they're asking you to measure. So it says we do the length together. So the length is L, and you can see it right here. So we're going to measure that together. So I'll take my ruler, you can take your ruler, and we're going to measure the length here in centimeters. Remember, centimeters are these ones over here. And I can zoom in. You can't really do that on your paper. But what you want to do with a ruler is line up the very edge here, right, with the edge of what you're measuring. Here we go. So for me, it looks like I get about 11.1. Now I'm using a digital ruler. You can use, obviously you're going to be using a physical ruler, so you might get a different measurement, but it should be about 11.1. So 11.1 centimeters, could be 11.2 centimeters. And then when I've done all of these dimensions, okay, I'm going to figure out what the actual length of the court will be. Okay, so I know that every 2 centimeters is 5 meters in real life. So what I'm doing is I'm doing the math. I'll just do the math down here. Now there are a couple of different ways to show you how to find the scale factor. So let me show you first with a ruler. It says that every 2 centimeters represents 5 meters in real life. So if I have my ruler here, and these are 2 centimeters, really that's 5 meters, 5 meters, 5 meters, and I keep going. Until I'm right about here, right? This is my 11.1. So right now I have 5, 10, 15, 20, 25. 25 meters, and I almost have up to a full 5 meters, right? I have 1.1 of whole 5. So I know it's going to be at least 25 meters, but I have to figure out what this 1.1 is. Okay, so that's where sometimes the ruler doesn't necessarily work out. So what you can do is this is part of this hole here, right? So I take these 2 centimeters and I say this is 5 meters, and I have 1.1, okay, of those 2 centimeters covered. That's how much, right, as a fraction, that much is. So what I can do is then multiply that by 5, because the whole thing is 5 meters. So if I want to figure out what the actual meter is, I can show how much I have, and then I can use that as a fraction compared to like the whole amount, and multiply that by 5. So this would be 5.5 over 2, which is 2.75. So I know that if I take this and this together, it would be 27.75 meters. Okay. Now, let me show you an easier way to do it. Or you might like that way, but let me show you a different way to do it. So instead of using the ruler, we'll just put that ruler off to the side. I'm going to figure out what my scale factor would be with this scale. So I know that the ratio is 2 to 5, 2 centimeters to 5 meters. And this is going to be the scale, well, we'll say it's the drawing, to the actual. Now I'm going from something smaller and I'm making it bigger. Right? Now it's not like a 1-to-1 swap. It's not like I'm multiplying it by 2. It's every 2 centimeters is 5 meters. So it's a little bit more difficult in that we're not going to have a whole number as a scale factor. So we have to figure out what we're multiplying by to get there. And to do that, you do the number that you're looking for, the actual, divided by the number you have, which is the drawing. So my scale factor is going to be 5 over 2, or you could say it's 2.5. So that's also called the unit rate. If you wanted to figure out, if we go back to the ruler here, and we zoom in, if this, right, 0 to 2 represents 5 meters, and 0 to 1 would represent half of that, which would be 2.5. And once you figure out what 1 centimeter represents, it's much easier to figure out what, 11.1 centimeters represents, because you don't have to use this fraction. So we have 1 centimeter, you could also say, is 2.5 meters. So you're going to use that information to fill in the rest of the chart. I'll let you do that now, and we'll see if our measurements line up. So what you should have gotten is that the width of the court was 6 centimeters, and the hoop to the 3-point line is 2.8 centimeters, and the 3-point line to the sideline was 0.4 centimeters. And you can take all of those and you can multiply them by our scale factor of 2.5, or 5/2, and you should get 15 centimeters, 7 centimeters for the hoop, and 1 meter. Sorry, this should be in meters, not centimeters. And remember, we're trying to go back to the main lesson, which is the main question, We want to know if it'll fit in a 20 by 20 meter square area. And if we look at this actual length, it says it's going to be 27.75 meters, so it does not fit. So we showed it with math, right, that it will not fit in that area. And don't forget to explain your reasoning down here as to why or why not it will fit. This last part of activity 1, the Are You Ready for More, says that on an actual basketball court, the bench area is typically 9 meters long. Without measuring, determine how long the bench area should be in the scale drawing. So we have now our, and if we remember our scale factor, our drawing to our actual was 2 centimeters to 5 meters. Well, now it's saying let's reverse it. You're given the actual area and you want to figure out what the drawing is. So now I'm flipping things around. So I kind of have to reverse it based on what I'm looking for. So let's see how I want to set this up. So just like when we were doing 1/4 and 4, how when we want to, say for example, go from one object to the bigger one, we multiply by 4. And if we want to go the other way, we would do the opposite of multiplying by 4, which is multiplying by 1/4. We're going to do the same thing here. We're going to use the reciprocal. So our actual scale factor was 5/2, our real scale factor, but now we're going to do the reciprocal, which is 2/5. So if something is 9 meters long, and I'm trying to go the other way around, I'm going to multiply 9 by 2/5. Because that's my scale factor going backwards. And I get 18/5, which would be 3.6. So in the scale, it would be 3.6 centimeters. And if you go back and you draw the bench, you can, or it's already drawn for you, you can check and see, is it actually 2.6 centimeters? And it should be about that. So now we're on activity 2. So activity 2, we know that the proposal does not fit. Okay, so your job is to sketch using the scale factor of 2 centimeters to 5 meters, your own basketball court that will fit into this area. And you can use grid paper if you want, or you can just do it right here in your book. But remember to make sure you label things. Okay, you're going to label things just like they did, like they labeled the length of the court, the width, right? Half court, things like that. So not only label it, but give it, dimensions. Okay. If you want to use a different scale factor, you can do that too. Like if you want to do 1 centimeters, 5 meters, you can do that, but you have to make sure that it fits within the 20 by 20 meter park area. Okay, so that means that it can't be, nothing can be bigger than or longer than 20 meters. So in this lesson synthesis and cool down, we've gone through a proposal of an actual basketball court drawing, tried to make it fit, or saw if it could fit into the proposed area, and it couldn't, so then we had to make a new one for Karima to use. Now, let's just kind of like synthesize that into one set of information, see if we can answer this question. So it says, how could you use Karima's scale drawing to calculate the actual diameter of the center court circle describe your strategy. So I want you to do that and describe your strategy in the box where it says share with my class. And I also want you to do the cool down as well.